Good afternoon to everyone in Australia, at least. It seems my countdown for my streams is broken. I guess I need to take a look at that. Yeah, it's been a little while. It's taken me some getting used to how this all gets set up again, but hopefully everything is working. Please, if you are watching this live, please let me know if you notice anything a bit weird. I'm a little bit out of practice, but hopefully things go fairly smoothly. Yeah. It's been a while. Lots of stuff has happened. Just as a quick, update on some other things. I am now married. My wedding was in October, and it was great. It was amazing. It was so good. And so with that, and also there has been some medical stuff going on with some close family members, and I have needed to spend some time kind of seeing to that. So that's kind of taken some time away, as well as, perhaps unsurprisingly, Jugglebot, at least at the current stage, does not pay my bills, and so I have an actual job, and that has been taking up a little bit of time lately, but still, I'm using every available moment that I can to get to Jugglebot stuff, and I've never felt, the more that I work on Jugglebot, the more confident that I get that it will work, and that it will be where I want it to be eventually, with just enough patience and work. Yeah, so we're getting there, but I understand that this may not be going as quickly as some other projects may, but we're getting there. Anyway, we've got a lot to catch up on, and I have done my best to kind of consolidate everything into these slides. To be honest, part of the reason why I've put off doing a stream for this long is because I'm just a bit intimidated by how much I have to catch up on, how much I have to catch everyone up on. I reviewed the last stream that I did either this morning or yesterday, and I was a bit like, oh, there's a lot more here than I thought since I last did a stream, but hopefully this covers most of it, and hopefully you're not left questioning like too much of the specifics. I've tried to do my best, and I also want to, I don't know, make it known that I only thought of doing this stream yesterday, so like 2 days ago I had no intention of doing this at all, and so this is all kind of, I don't know, strapped together semi-last minute, so yeah, but it should, yeah, hopefully it all works well. Hello Batboy, it's good to see you, very good to see you again. Alright, got to get used to all my buttons again, so yes, lots to go through. Alright, first thing, and most kind of following on from where we left off, is that Ball Butler now works. And there's obviously different ways, that, like different degrees to which I could consider it to be working, but I would call this quite good. So let me just, I've got a couple things that I want to demo today, and I have been trying to make sure that they all work nicely. So I wanted to show you this thing first. So one very useful ability of Ball Butler, which you can see up on the shelf over here. One thing that it needs to be able to do is to reload after it's thrown a ball. This is literally the entire point of Ball Butler, is that it can have a storage area, a hopper of balls, which you can see if we go to this camera. Nope. Yeah, actually you can see it on that one. Okay, ignore the white bar, that shouldn't be there, let's get rid of that. So up, oh my god, this is all reversed. Up there, you can see there's like I'm gonna get rid of that because it's confusing. There's like a rail, and in that rail is, I think I have like 10 balls in there. So the whole point of Ball Butler is that it will grab a ball from that rail, and I'll show how that works in a sec, and then it'll have that ball ready to go, and then when Jugglebot needs the ball, so either Jugglebot has dropped or it's about to start a multi-ball session, Ball Butler will throw the ball down to Jugglebot, reload itself so it's ready to go again, and it's all good to go. And yes, as Batboy has mentioned, there are some videos on Zulip that I was posting as this was kind of being developed, and yeah, so if you want any, there's definitely some information on Zulip that I'm not going through explicitly. Well, I'm not intending on going through explicitly in this stream, so if you're curious to find out more, definitely check out Zulip. There's some stuff on there that's interesting. All right, so let me show you how this works. So hopefully you can hear me as I move around. My microphone should be moving with me. What do I need to do? I'm going to unplug yeah, I'm going to unplug Jugglebot for a moment and plug in this instead, which I'll go into more detail in a sec as to what that is. Ball Butler now has its own independent e-stop, which is very nice. It's over here. That's actually my motivation for doing that. I think I mentioned this ages ago and I was debating whether or not to do it. But I decided to do it just because it really wasn't that much work to do. My primary motivation was to be able to turn Ball Butler off. If Ball Butler's doing something that's evidently wrong, like honestly, there's not really much that it could do wrong, but if it's like, I don't know, pushing limits or like running into the wall or something like that, then I can hit the Ball Butler e-stop without having to affect Jugglebot, because the last thing that I want to have happen is Ball Butler is like running itself into the wall. Jugglebot is in a position where if its power got cut off, it would collapse in a dangerous way. And then I hit the global e-stop to stop Ball Butler hitting damaging the wall, and then Jugglebot collapses. It's just like, there's just too many things to kind of manage. Someone did raise a concern with like a kind of counterpoint to what I just said, which is that if I have two e-stops, then it becomes a matter of like, oh shit, like I have to like have a thought process of like which one do I use depending on what the problem is. But I don't know. I think that that is a better problem than the former of the two robots both not wanting to, well, one robot needing to be turned off and one robot not being able to be turned off. That's a bad problem to have. So, and also it's nice so that when I'm doing work on just Jugglebot, I can just turn Ball Butler off and it won't do its like startup sequence every time. So, Ball Butler is on and global e-stop is now on. So Ball Butler will do like a little booting sequence thing. Let me turn you to this view. All right, so it just homed. Obviously, it didn't move very much, but it doesn't need to. What do I want to show? Reloading. So I'm very happy with it. I'm super, super proud of this. Ball Butler now has a sensor in its hand to detect when the ball is there or not. I debated long and hard as to whether or not I should do this. Oh, I'm blocking the camera, sorry. I debated long and hard whether I should do this or whether I should just have an automatic, like, ball has been thrown, therefore hand must be empty. But I don't know. I don't like running these hands in the throwing pattern without a ball in them, because they kind of depend on the ball's inertia to, it's like part of the planning of the trajectory is that the ball inertia is there. So if the ball is not there, then the hand runs a bit harder than it should when it's empty, and it does some bad things, and I don't like it doing that. Yeah, so now, and so what this does is you can see when I take the ball out, it tips forward. And the reason it tips forward is because sometimes the ball can be in a spot where it's not being detected. And I'll go through how this detection works in just a sec. But there can be some situations where the ball is in a spot where it's not being detected. And by tipping forward, it kind of like centers the ball over, there's a limit switch in there. And it centers the ball over the limit switch, forcing it to depress the limit switch. Yeah, and once after it tips forward, if it detects, yep, there's still no ball there, then it will go through the reload sequence. Yeah, which is very cool. I like this a lot. If you're wondering, there are some problems with, like, if I put a ball, that was a bad example, when I'm like reloading the reloader, if I throw a ball like there, so it's stacked on top, I guess we'll see over the course of the stream whether that fixes itself, but they should usually fix themselves. If the balls are stacked up, sometimes there's like one failure mode where the balls can get kind of jammed as they're rolling in, but I don't know. Having followed the Wintergarten project for some time, I am very well aware of how deep of a rabbit hole funneling balls can be, and I figured this is good enough, and if it's a problem, thankfully I'm tall enough where I can just kind of tap it and fix it up. So it's not really that big of an issue. And it doesn't happen very often. Okay, so how does this work? Well, as I mentioned, there is a censored hand, which is lovely. And I'm going to turn all these fans off. Yep. Oh, there's so many things to check. All right, so let me show you Ball Butler. There is a link in the description, as always, for the CAD here that I'm showing off right now, so feel free to check that out if you want to see it for yourself. Yeah, some things have changed with Ball Butler, but honestly, I think the most exciting thing is the censored hand. So actually, before I show you how this actually is implemented, I want to go through the process that I took to get here. So I'm calling this the haptic feedback because, I don't know, it's a nice phrase. And I went through a couple iterations of this. So basically, the basic idea here, maybe before we get too crazy, is to... I swear I had them around. All right, I put them somewhere that I've forgotten about for the time being. Anyway, yeah, okay, I guess here's an example. So in the hand, there is a switch, and rather than just like a plain old limit switch where there's like the bar that gets pressed, yeah, hopefully you know what I mean. Rather than using an actual limit switch, I've decided to actually use a keyboard switch. So in here is a very small, well, a normal size, but like very thin keyboard switch. And I've used those because I figured that I wanted something that can depress it can kind of be pressed like evenly around the whole thing. Because if I'm using like a normal limit switch where there's the bar that gets pressed down, if something's kind of coming at it from the side, I figured that sometimes that might get caught up or like a bit bent, and there's like a lot of travel that it has to go through, so it's a bit more kind of in the way of the ball being centered in the hand. But a keyboard switch, it's smaller. I can make a little button on it to like allow this to be depressed in here. And also, importantly, not so important for Ball Butler, but definitely for Jugglebot, if I'm going to be bringing this into Jugglebot, which I intend to, but I haven't yet, this needs to be able to survive quite a beating. This will have balls landing straight on it from up to like, I don't know, 5 to 10 meters high in the limit, landing directly on, ow, I just cut myself, landing directly on that switch, if it was like perfectly tuned and everything. So this switch needs to be able to kind of handle a beating. And I figured, you know what kind of switch can take a beating and is like quite robust? Keyboard switches, because gamers be crazy. So I've decided to go with the keyboard switch, and that sits inside the hand. But the problem is, the hand moves up and down, and I need to get that signal from that switch, whether the switch is open or closed. I need to get that from the hand out through this moving channel to the controller. And in this case, it goes the whole way through down to Ball Butler's like brain, I guess. Yeah, so that presents a couple problems. There's a couple different ways to solve that. And this is something that we talked about a lot, like over a long time. And I've always been quite hesitant to do this because I really didn't want to add a cable solution. I don't want to have a cable that runs from somewhere out to here that then moves up and down, and like that's going to get caught on something. This is zipping around really quickly, and there's a lot of stuff around both Ball Butler and Jugglebot. There's just a lot of things for that cable to get snagged on, and yeah, I don't want to have to deal with that. So that kind of forces us to use a... my thumb's actually bleeding now. Yeah, that kind of forces us to use something to transfer the electrical signal from this rail onto a static element. And I've had a couple, I came up with a couple ideas for this at first. Sorry, I need to get a band-aid for my thumb so I stop bleeding everywhere. Give me 1 second, I'm gonna put you back on the broken loading screen. Okay, should be good. Sorry about that. Yes, so I've had a couple ideas for how to possibly implement this, and my first idea was to use a phosphor bronze finger, where I bought these. Well, I bought these brass sheets off of AliExpress. I don't know, they're exactly what you would expect, just thin brass sheets. And my idea was to have a long PCB kind of rail that would sit along like the hand, and one of these rails would be for one side of the switch, the other rail would be the other side of the switch, and these phosphor bronze fingers, which are actually the things that implement on here, and is actually the thing that I just cut myself on. You can see them along, like it's like tucked into the side here, and then goes underneath, and is supposed to be bowed so that it makes contact with the PCB, and then on the other side it tucks in as well. So hopefully you can kind of see that. It's very, very fiddly to make, super fiddly, and is very sharp, which is how I just cut myself. And yeah, no, that didn't work. This is as far as I got with that. I installed it and I measured the continuity, and I realized that there is no continuity because the bowing is not quite strong enough. So on this side, you can see, I don't know if this is going to come up too well on the camera, but the phosphor bronze kind of finger thing does contact over there, but on the other side, it just doesn't. I don't know if you can see that. There's a slight gap. And more importantly, the actual carriage that runs on the linear rail itself is metal. So with the way that I've attached this here, where you can see like this part of the phosphor bronze, come on, focus. This part is touching the metal, is touching the carrier, and that part is also touching the carrier. So this doesn't work. This doesn't like allow this doesn't allow the switch to do anything, because this is always being continuous between the two sides. The intention here was that one side would be attached to one side of the switch, the other side would be attached to the other side of the switch, and then it would do what the switch says. But because these are always continuous, the switch is basically being ignored. So this was very fiddly, didn't work, and yeah, it didn't work for two reasons. Like, yeah, it was very problematic. So I turned to the internet and I said, surely someone has done this before. Surely someone has had like a moving thing on rails. How does that work? And I did think of like slot cars that you have when you're, I guess adults play it too, but I was familiar with it when I was a kid, where you have like a little controller and you can like change speed up or down with your little trigger thing, and your cars zoom around the track. And I was looking into those a bit, and then I saw that the YouTuber Engineezy had encountered a similar problem to this, and he used pogo pins, which are the small little pins that you would see in like if you've got like little earbud chargers or anything like that. They're the little brass pins that stick out and they're kind of springy, and they conduct electrical contact, or electrical current. And that's what Engineezy used when he made a Flappy Bird game thing, like a real world Flappy Bird. It was kind of cool. I'll put a link in the description for that video after the stream is done. I forgot to for now. But it's easy to find. And that worked really well for him. And I was like, cool, this seems like job done, easy peasy. But then I realized that Engineezy's, his requirements were quite different to mine. He just wanted a thing to carry electrical contact when these things were moving very slowly and probably not too many times around this circle. I'd be very interested to know what his thing looks like after he's finished playing with it. But my situation is I want this thing to cycle extremely quickly and hundreds of thousands of times. It needs to just keep on working. And importantly, it has to ensure that we have continuous contact the whole way along. So if the ball is in the hand and the switch is depressed, that should register when we're down here, and when we're up here, and when we're over here, and when we're here, and the whole way along. Even as we're moving, let's say that the ball was like taped into the hand or something, that should constantly be reporting ball in hand as this is zipping around the entire time. So what did I do? I made a test. And that test rig was this guy here, which is basically just the hand actuator by itself. It has an Arca Swiss plate, which, oh my God, if anyone's doing anything at all related to like any robotic stuff, Arca Swiss is so freaking good. Everything that I have has like Arca Swiss plates on it. It's what I'm using to mount the catching cone, everything. Arca Swiss is amazing, it's so good. The cameras, they're all there. Wow. Anyway, so this is my test rig, and this basically would run the actuator up and down, up and down, up and down, with the readout from the hand sensor constantly being checked 1,000 times per second. And what this check would do is it would say, throughout the entire stroke of the whole thing, how many frames per stroke were dropped. So what I would do is I basically wired the two wires together so that the switch was always connected, and then it would run, and any time that we lost continuity between the pogo pins and the PCB, that would register as the switch is disconnected, and then that would count as a dropped frame, because they all should be connected because I literally wired the wires together. Yeah, and I let that run for some time. Yes, super rad maker, this is absolutely still the juggling robot. We're still getting there. And so this was the result after, I want to say 70,000 cycles in the PCB trace, and that's actually the PCB that I have here. So, I mean, I'm probably not going to be able to show it much better than the photo can. So you can see that some pretty significant marks were left behind on the PCBs. And this is the result of how many frames were dropped. So this on the y-axis is the percentage of frames in the entire up-down stroke for one stroke. How many of those frames were reported as being discontinuous, i.e. the pogo pins were not making reliable connection to the PCB, and how many of them were good, how many of them were correct. And so the drop rate should be 0. And you can see here, this wasn't the same session because it took quite a long time to do this. So you can see it was really interesting actually. Very, very early on, like in the first couple thousand cycles, the drop rate went quite high, and I was a bit like, oh, this is working a lot less well than I thought it would. Maybe there's a problem here. But then it went away, and for like 4,000 to around 10,000, it was completely fine. No drops at all, perfectly, perfectly continuous connection the whole way through. But it started getting really, really loud, and in hindsight, I should have found a video to show you in the stream now, but actually, while I'm here, one thing I just want to mention is that I do 100% intend on making a video on Butler. Maybe I'm thinking actually 2 videos, but I'll talk more about that later. And there is definitely stuff that you will be curious about that I will not be going into in detail now, unless you ask, and depending on what it is, I might be able to find it. But all of this information will be in those videos when they come out. But yeah, this made a horrible, horrible screeching sound, and yeah, I had to stop it. So then a couple days later, when I just had to do some other stuff for a couple days, I then applied some highly conductive grease to this. And this stuff is, if I can find it, it's quite interesting actually. HCG, highly conductive grease. And it's got like copper in it. I think I might have shown this off before. Come on, camera. There we go. That stuff. So I put some of that on, and you can see that the results really were not amazing. And it just kept getting worse and worse and worse and worse. And at some point I decided to reapply the highly conductive grease, and you can see that the drop rate did go down quite a lot, but that really didn't stay for very long. And I thought I had a photo. I should find this. I've got a photo of what the pogo pins looked like after doing this, and they are not amazing. Oh no, where did I put it? I thought I got it out. Yes. Yeah, here we go. Sorry about the wait. There's always more stuff that I forget about. But this was the result afterwards. So you can see these were both originally fully kind of like curved on the top, and you can see definitely the one on the right has been well and truly flattened. And I think that this is related to why why there was this peak in drop rate, which then went down. I reckon there was a slight, I don't know, it might have even just been something like a piece of dust or like a slight inconsistency somewhere on one of the pins that just had to get worn down just enough to make like full like surface contact. And then after that, I don't know. I'm convinced that there's like some kind of like skipping going on here, but I don't really know. I haven't analyzed this closely with my slow motion camera. It'll be way too awkward to do. And also I don't really care too much what the actual problem is. I just know that there is a problem and like it's not feasible to solve it. I did consider using multiple pogo pins on each channel to kind of like spread the load across the channel, across the rail, but I don't know. So at this point I was a bit like, oh, like I don't really know what to do here. Like surely there's another way to do this. There must be some other example of like conducting electricity over a moving contact. And maybe with that framing, you might have thought of it yourself, and also kind of shown it a little bit in the slides. But actually Claude suggested this, which was to use carbon brushes, which are the brushes that are used in motors to carry the electricity through the rotating rotor of the motor. Yeah, and that worked exceedingly well. Like so well. I did need to file down my carbon brushes to make them small enough to fit in the position that I planned for them. But the end result is that I can't remember off the top of my head how many cycles this went through, but it was easily 100,000. And I've got like 15 hours of footage, like what I'm about to show you if this file will open, of the hand just going up and down, up and down, up and down. Not a single frame dropped the entire time. And this just goes for hours and hours and hours and hours. And it didn't make a terrible screeching sound, which is a massive pro. So yeah, this was only one of the sessions. This one went to 45,000 cycles. I'm fairly certain overall I went to like 120 or 130,000 before I decided to call it. And I remember converting that into meters, and it was something ridiculous, like 50 kilometers or something. Like, I have no worries at all about now this hand actuator, because this is the most rigorous testing that I've done on the actuator itself, as well as on this form of sensorized contact. And to actually show you what this looks like, now we can go to the CAD. So to show you how this is implemented, I love how this looks. It's so nice. So you can see I've bought on Amazon, on AliExpress rather, some carbon brushes, which I can show you. Interestingly, some of them come with springs and some of them don't come with springs. And annoyingly, the ones that came with springs didn't come with contacts to the actual carbon brush, but the ones that did not come with springs did come with the... it's a whole thing. So this is what they look like with their little contact on them. So this little like brass strip is what you can solder onto, and that is then electrically connected to the carbon brush. But then I also have these ones, which are a bit smaller, which are the ones that I actually used, which don't have the brass like braid on them. But thankfully, without too much hassle, I was able to squeeze the, I got some, what is it called, solder wick, and squeeze that between the spring and the carbon brush, and that seems to work pretty well. And yeah, so I have those, and they sit inside these little channels in here. So you can see they're actually in the CAD. So can I hide? Yes. Yep, so these are the carbon brushes here. So one of them, yeah, there's one for each channel. And there's not a huge amount of clearance in here, but it seems to be enough. And so the good thing about these is that they have a spring on them, so that way as they wear down, which I'm not convinced will actually happen on a big scale, because I actually did measure them. I measured the height of the carbon brushes before and after the 100 and something thousand test, and it was like 0.5 millimeter of difference. So I don't really think that wear is a real problem in this. I think that as they run, they kind of like lubricate the channel, and they just like sort themselves out. It's so nice. But yeah, so they sit in there, and you can see they're like the pins that go to the keyboard switches, they each have their own channel that the wire runs through, and yeah, fairly straightforward. Definitely not fairly straightforward to CAD, but fairly straightforward in principle. And there's a little button keycap thing that actually presses the switch. And that also has like a small amount of tolerance, but not too much. This tuning the height, like the size of this little button was actually a bit of a process, because if it's too far out, then that means that when the ball is in the hand, the ball doesn't sit like straight in the hand. It gets kind of like shifted to the side by the button pushing into it. But if the button is too small, then it won't detect whether the ball is in the hand at all. So it took a few tries to kind of like adjust that to be correct. And I feel pretty good about it now. So when it's fully depressed now, it's actually underneath the surface of the hand. And when it's up, it's fully extending above it. So yeah, that's how that works. As for actually reading the sensors, the signals here, this then just goes to 2 of the GPIO pins on the O drive. And I've set up a thing to basically read from those periodically. So I can get very accurate. It's not 1,000 times per second. The 1,000 times per second was only for the test. I'm now reading, I actually don't remember off the top of my head, it's on the order of like single to tens of hertz, so it's not super fast. Yeah, as I said before, I have not yet implemented this on Jugglebot, just because it's a bit of a faff, and I've kind of had other things to do, but I fully intend to at some point. This is such a nice upgrade, and I wish that I was aware of a solution like this back when I was doing Jugglebot's hand, because I really would have done it this way if I had known about this, but you know, I guess that's the process of development. Yep. Okay. So that's how the censored hand works. Yes, so Ball Butler does work, and as I've shown, it can detect when the hand is empty, and it can reload itself, and it can do all of that, and it's great. But it isn't, by default, super precise, which is kind of annoying. So what I mean by this is fairly well explained in this plot here. So, So this plot is showing, this is kind of like looking down from above, the results of me commanding Ball Butler to throw to a grid of points. So all of the X's are the points that Ball Butler was aiming for, and then all of the dots are the points where the ball actually landed when it was being thrown to that specific target. And the bigger dots is like the average of the cluster. And the arrows are showing how you get from the cluster to where it's supposed to go. And you can see, that there are some positions where the accuracy is very, very good, like this yellow one in the first column, as I don't know, tennis ball color, I'll call it, where they're all like pretty much spot on. But then as we get further and further to the X, like in the X direction, and also just like generally further away from Ball Butler, the accuracy shifts quite a lot, to the point where like way up here, it's what, like half a meter away almost. It's very, very far away from the target. Yeah, so, but the good news here is that the clusters are actually quite tight together. They're obviously not perfect. Like some of the clusters, like this purple one over here, I don't know what that spread actually is. This is just a PNG, so I can't actually interact with this plot, but that's maybe, I don't know, 20 millimeters, 30 millimeters, like kind of far, to the point where it might actually be a miss, but they're pretty close. They're close enough that I was happy to kind of call it there. Annoyingly, now I really wanted to show you this and actually like demonstrate this in operation, but annoyingly, somehow, since having done this, I've like lost / forgotten how I went from this correction to applying that correction onto Ball Butler, and I need to go through that process again. I only realized this like a couple of hours ago, and I was like, oh no, I can't show the demo off as nicely as I want to, but it did work. You got to believe me. And I actually do have a video of some of the first throws from Ball Butler to Jugglebot. This was all super janky, very hard-coded. Well, at least the Jugglebot side of things, like where it goes and how it kind of collects. Definitely not how I want it to be done in like the main production branch, but it actually, I was just kind of testing the hardware out here. So I should have found some timestamps here, but you can kind of, I don't know, watch me while I work until I get this going. All right, here we go. So Butler is centering itself, getting ready. Got to send a command to get Jugglebot to get ready, I think. Yeah. So Jugglebot goes up and gets ready. Jugglebot does a little tilt to make sure that it's perfectly like in line with the direction of the ball as the ball comes in, and then it should catch. As I indicate there, very close. Some of these did work though, and it's a little bit kind of hit and miss. This is why I'm saying this is not how I want it to be done in prod, because sometimes it does miss, and Jugglebot will need a way of reading, like there we go, that one caught. Jugglebot will need a way to adapt to Butler's throws being just a smidgen off, because you may remember, and I'll show this off very soon, I have motion capture cameras in this room, and they are tracking everything that is reflective, everything that is kind of that grey colour. And we should, in principle, be able to use that to say, okay, Butler tried to throw here, but in fact the throw was just a little bit off, so Jugglebot needs to accommodate for that by moving just ever so slightly to make the catch. That's a big part of what I want to add. And I feel very good that with Butler's consistency, even though it's not perfect, it's consistent enough that Jugglebot should be able to make that tiny little correction, be it an orientation or a position correction, to make the catch. So I'm not too worried about over-optimizing Butler's accuracy. I think that what we have in these plots is more than good enough. Now, one thing that I want to show you with regard to this plot is how I actually got this data, because this was not a trivial process and is a big reason why I am putting off doing this again until after the stream, at least. I was considering doing it today, but it takes a while to do. So let me show you what this looks like. So here's a recording that I did where I basically commanded, I had like a series of positions where it was Butler aims for, I don't know, let's say the first X on this grid, whatever that coordinate is, this red spot here. It aims for that spot and throws 10 times. Each time it reloads and throws again. So each time there's probably, I think it was about a 2-second interval between each one. It would throw, ball would land, ball was being tracked the whole time, and then it would do that again 10 times, it would change to the next target. Keep in mind, each time it does the throw, it has to reload every single time. So it's not like it can reuse the same pose that it's in before it throws. It has to go through reload, reposition itself, and then make the throw again. Which, to be honest, like I'm kind of surprised that the accuracy is as good as it is, given that it has to reposition itself every single time. It's quite good. I'm quite happy with it. But yeah, so these recordings took quite a long time. I think, what is this? 860 seconds, whatever that is in minutes. And if I can show you what this actually looks like. So actually, maybe just first off, in real time, we can just see it just briefly, and then I'll show you the big plot. So we have Butler in the frame and very annoyingly, I really wish that I had like one more motion capture camera, but I kind of suspect that's always the case. You always want one more. But I want one for Butler, because Butler can orient itself in certain positions, like when it's reloading and when it's in its, I think like where it is right now, it's like just out of view of the cameras so that it doesn't get picked up as like a rigid body. There's not enough of its markers being detected, which is a bit frustrating because it kind of like leaves and enters the scene. But yeah, you can see here it basically throws and the ball lands. And something that's very cool in this software is you can show the trace. So as the system goes, I can't remember how to fast forward. But yeah, you can see the ball goes along. But the cool thing is that we can extend this trace out to be the entire plot. So you can see every single throw. Wow, look at that. How good is that? Now this data was not remotely this clean when I started. Cleaning this data took another, I don't know, 10 or 15 minutes. Because you got to remember that Ball Butler's hopper of balls only holds, I think I only have like 10 or 12 of these balls in total with the retroreflective tape on them. So every 10 throws, I would have to throw all the balls back up into the hopper. But of course, when I'm throwing them back up, they're also being tracked. So there's a lot of noise in this data that I had to clean up. But the result is what I think is very clean. And so once I had this, you can see that like to every single position that it's throwing to, the clustering is quite tight, which is very good to see. And then this got passed through a Python script that then took out all of the landing points and compared those against the suggested, like the target points. That was also a bit of a process, but it's not worth going into that right now. Yeah, I think, actually no, sorry, there's one other thing that I wanted to mention on Ball Butler. So this is all well and good. Everything that I've talked about is all well and good for spatial accuracy. And we can see with this plot that the spatial accuracy, as I said, it obviously needs a correction to be applied to it. And by the way, the correction that that I was using before to make this actually work, which I need to re-implement, is an affine transform, which basically, from my understanding, please correct me if I'm wrong, it basically takes like you can imagine it as being like you have a grid of points that are all nice and even, like the x's in this plot, and then you have another set of points that needs to be scaled in some way. And as far as I'm aware, the affine transform is kind of like the most generic or the most arbitrary transformation you can have, because you can scale, you can rotate, and I guess that's kind of all you need. Yeah, but you can move the one set of data in basically whichever way that you want to kind of map them over each other. And so that's what I did here, is I fit an affine transform from the landing points to the target points, and then we can use that and apply that to every single throw that is done in the future, and that should hone it right in. And it does, when I remember how I've implemented that. Yep. But as I said, this is all well and good for spatial accuracy, but it doesn't tell us anything about time. And for juggling, time is at least as important as spatial accuracy. Because if you throw a ball to the right spot, but you're like 2 seconds too late, you may as well have just completely missed. And if anything, it's actually probably going to be worse, because you're going to be like right in the middle of things, and you're going to have collisions and all sorts of problems. So we need to make sure that the timing of this is good as well. And I actually did post on Zulip about this at the time, and I showed some plots, but the way that I was doing things back then was I was using the motion capture data, this that I showed before, this stuff, and we compared at what point, like we compared the time when the ball passed the catching plane, like the plane where the catching cone was. We compared that against when the ball should have landed based on the command. And I got some data from that, but I don't know, I was never super convinced by that, because it's kind of like too far removed. Like I'm using mocap data where the clocks might be slightly out of sync. They shouldn't be, but they might be between ROS and the mocap. And I don't know, it felt kind of too abstracted. So what I've made just in the last like 2 days is a censored catching cone where, let me unplug it. The old catching cone, you may recall, was pretty straightforward. It's just 5 markers, and these are used so that the cameras can see where it is. And that was about it. And an Arca Swiss plate on the back for good measure. But the new one it has the exact same marker position, which is nice, because that means in the motion, when I'm using these, I can interchange them and the system doesn't know or care which one's which is very convenient. But it also has on the back, I've got a Deutsche plug to plug it into the CAN bus. We've got a Teensy, and we've got a piezo contact sensor in here. Now, I did need to make sure that the piezo sensor would not destroy the Teensy, because when you hit these sensors, they can generate spikes of up to like tens of volts, and the Teensy is only happy with up to 3.3 volts. So I've got a Zener diode in there and some resistors to make that work. And now, in principle, this should, if if I have this connected in, I can read from this and I can say, okay, as the ROS system, I have commanded a throw to be at this position, at wherever the catching cone is, at this specific time. Does the ball actually land there at that specific time? And now we can test both of those things. Because if it landed in the cone, then it was spatially correct. And based on when the sensor is hit, the Teensy reports a signal over the CAN bus to say, hey, the sensor was hit at exactly this time. The Teensy's clock is synced with the ROS clock. So it's all perfectly within like tens of microseconds. It's all correct. And then we can know how like early or how late or how spot on the throw was. So let's try this out. Now, as I said before, I haven't had a chance to reapply the correction on Ball Butler. So I've had to just kind of find the throw values that work to get it to land in the catching cone for where it is right now. If I move that around, it's not going to work. But hopefully me removing it just then was not too much of a movement. So let me show you. Maybe actually just before, I shouldn't be showing there. Just before that, I just want to actually show you, just so that you know what you're looking at here, I want to show you my new GUI that we've made as well. I wanted to show this off later, but now's a good time. My old GUI was kind of crap. You may remember it. There's no point thinking about that too much. It's gone. It's dead. This new GUI, amazing. It's so good. I can see all the data synced on here. It highlights on Jugglebot which axis we're showing here, and same thing for Ball Butler. Maybe if I get rid of me so you can see the whole thing. It's so good. It's amazing. And so what we're going to be using here, importantly, one thing that's useful is we can see what systems are connected and what's actually live. And importantly for us right now, we're going to be looking at the catching cone because we want to see how early or late our throws are. So let's just double check. Ball Butler's e-stop is on, or like disconnected. We can turn on the whole thing. Jugglebot is no longer connected because I only have 2 CAN cables right now. So right now one of them is going to the catching cone, one of them is going to Ball Butler. And let's go to, I don't have a camera view set up so you can see the whole thing, like everything at once. But let's go to the Jugglebot view first because it's more exciting. I just realized I'm blocking the view here. Let me move me up here. All right, so let's see if this works, and then I'll show you the result in the GUI. So I launch. Actually, maybe while I'm getting this set up, you can see my VNC screen, just so you can see what I'm doing. And we want to throw a command. So this is what I calibrated earlier: the specific yaw angle, the specific pitch angle, and the throw speed to get it into the cone where it is right now. However, if I try to run this right now, nothing will happen. Well, nothing should happen. Oh, oh, I'm mistaken. All right, let me go back. All right, nothing should happen because Ball Butler has not been calibrated yet in this session, and we can see that in this view here on our GUI. We can see Ball Butler is here, but it's not been calibrated. And what calibration means is, no, don't save that, is that when Ball Butler shouldn't move around, really, when it's in its spot. It should be exactly in the same spot every single time. But, you know, this shelf that it's on is not really very stable. Like, things can change, and if I take Ball Butler off and put it back on, it might be in a slightly different position. So we need to know exactly where it is in relation to the rest of the room so that it can make accurate throws. And the way that this works, I really wanted to have an animation to show this, but I haven't had enough time to actually put one together. But the way that this works is we have on Ball Butler, I'm really happy with this idea. On Ball Butler, we have 5 tracking dots. So we can see these here, 1, 2, 3, 4, 5. And to allow us to find out where the platform is, where Ball Butler is, we assume that like this kind of plate, the yaw axis, we assume that this is parallel to the ground, which is maybe an assumption, but I've checked like the cupboard levelness with respect to the ground, and it's very close. And so making that assumption allows us to do something that I think is quite clever, where we make Ball Butler yaw about, I think it's like 120 degrees. It stops and then it yaws the whole way back. And this should make all of these circles, all of these markers should trace out perfect circular arcs, because the yaw axis is just rotation. So all of these dots should trace out perfect circles. And where do those circles rotate about? Well, that's the center of the yaw axis. That is like the Z axis of Ball Butler. So if we find all of these circles as Ball Butler kind of yaws back and forth, we find all of these circles, and then we find the center point of all of those circles, and then take the average of all 5 of them, because inevitably there's going to be a bit of noise. As I mentioned, as Ball Butler moves through its arc, some of the markers disappear to the cameras and then reappear, so we don't always have full data on all of them. So we basically fit all these circles, find the center points, average all the center points, and then we say that is the center of Ball Butler. And so that tells us where the y-axis is in space. We can find the height of it based on the average of all of these 5 markers. That tells us the z coordinate. So now we've got x, y, and z. And if we assume that it's level with respect to the ground, then we know that. And because we've got encoders on the yaw axis and the pitch axis, we know what both of those are as well. So Ball Butler is placed in space. And so I don't really know what the best view would be for you to see this, but let's go. I'll show you the mocap view so you can see it kind of like coming in and out of the space. So you can see here we've got a few things in the zone right now. We've got the platform, Jugglebot's base down there, the catching cone here, and Ball Butler. And you can see if I add if I've got this other catching cone and I bring this in, that should. Oh, okay. I've actually, this is the first time I've tried this. I'm gonna guess that QTM, this software only allows for like 1 instance of each rigid body. I might be able to change that. I feel like I probably can, but yeah. Yeah, so this is all like live data. So let me also run, I want the GUI. So if I click calibrate, then we can see Ball Butler moves through its arc, and all of these points will trace out nice, neat circles. And if that has worked, which it has in this case, then we can see in VNC, we've got some stats on everything. So we've got how many samples each marker gave us, our uncertainty, the radius, and everything like this. And then it detects, it gives us some information as to like what happened in that calibration. And so we know that yes, that calibration worked, because we can see in our GUI, we've got calibrated. Nice. So now we should be able to make throws. I don't know why that throw was allowed before. I have implemented some stuff for like remembering the calibration. So I should be able to say, okay, Ball Butler hasn't moved in a while. The calibration should be remembered. I'm going to guess that's why that worked before, but it doesn't matter too much. What we're interested in is a catch. So what I can do is I can send that same command that I sent before, throw, and let's go to Jugglebot view so you can see that. Okay, that was very close, but not quite. And we can see that the ball did fix itself up in the hopper from ages ago. So now the hopper's nice and clean. All right, let's try that again. Throw again. Oh, so close. I'm just gonna move that just a smidge because we want the timing data, which actually I realize has also just come through anyway. There we go, smack bang in. And we can see in the GUI what this looks like. So we can see that that throw was 94 milliseconds late. And let me do another one so you see what that looks like. Oh, the ball is still in the hand. That one, 90 milliseconds late. I've only tested this a handful of times so far, but every time it seems to be around 85 milliseconds late or so. 92, yeah. So it's always consistently, it's consistent, which is good, but it's always just a smidgen late, which is obviously a problem, but as long as it's consistent, that's fine. Because worst case, absolute worst case scenario, I can just go, all right, throw 90 milliseconds sooner than you were planning to, and then it should work. Obviously, I don't want to do that, but, you know, sometimes you got to do what you got to do. Okay, cool. So that's what I wanted to show you there. So let me shut that down. Put this away. And go back to slides. All right, and I'm going to turn this off because the fans are loud. Okay, cool. Now, one annoying thing is that every time I do one of these runs, I've got to run around the room and collect all the balls and chuck them back in the hopper. So let me just... And I've generally gotten pretty good at chucking them in there, but sometimes I miss, and then I've got to go and fetch them again, which I love. So much fun. All right. Now, I've got some... So that's basically it for Ball Butler, I think. There's spatial precision was good after I tuned it. I need to go back and remember what I did there because that was a little while ago. Temporal accuracy, I've only made this censored catching cone is approximately 12 hours old, so I need to do a bit more testing with this to get it to work. I want to fix the spatial accuracy first and then do the temporal accuracy, but it works. It's connected to the GUI. I can get good data, so it's the foundation is there for me to finish Ball Butler and get it where it needs to be. So now we can move on to some Jugglebot stuff, and there is quite a lot of Jugglebot stuff to do. So to go through. So I was planning. At one point, I was thinking of having a video, like a live stream on Ball Butler to catch up Ball Butler stuff, but I started using Claude more. And I realized that maybe Claude is good enough to do what I've been wanting to do for quite a long time, which is to fix Jugglebot's control system and make it so that it can actually deal with things like the platform inertia and just basically have smoother motion. Because what I was doing before, you may remember, is it was so straightforward. I basically send a command. I would say, okay, the Jugglebot platform is here. I want it to be here. We can calculate what all the leg lengths need to be to get to there. Let's just do that calculation once and then send all of those leg lengths out to each individual leg to say, wherever you are now, get to this position that will put us in this pose. So each leg was doing its own thing. They were all operating on different time scales. They were all just like, yep, I'm just going to get to... It was down to the O drives basically to decide how they wanted to get from where they are to where they should be. And it was not like a holistic way of controlling the system. It was all just like each leg was doing its own thing. And that obviously worked and was okay for doing like Space Mouse control was smooth-ish. But doing juggling where you want to quickly get between different poses, you really need to be taking the whole system into consideration. We need to be looking at the platform inertia and saying, okay, can we just move side to side like this? Or maybe does it make more sense? And maybe it will result in less force on the legs if we do it slightly differently. Maybe we can tilt first and then go over. Maybe. Probably not just going straight across is the best way to go. And anyway, so I was using Claude more and I realized that actually Claude is very, very good, Claude Code specifically. And I have been sucked into this rabbit hole of improving Jugglebot. And there's a lot to talk about here. So before we get into too much detail on that, I wanted to just quickly have a brief little interlude on some other little things that I think are meaningful, but are a bit less kind of heavy than the Jugglebot work. So one thing that you actually may have noticed if you were really paying attention is that when Jugglebot starts, when I start a ROS session, we now check that all of the firmware on all the O drives is the same, or is correct, is what we're expecting it to be. So we can see here somewhere in this start here, yep, we can see so we can see that the firmware is what we want and that the Ball Butler has checked the firmware, it has passed the firmware check. There should be one for Jugglebot here as well, saying Jugglebot has passed the firmware check, but Jugglebot was not plugged in this session, so it's not there. And this may seem like a small thing, and in the grand scheme of things it might be, but this is actually very useful because I did have a problem, as you can maybe guess as to why I've implemented this. I implemented this because I had a problem where the firmware was not the same between two O drives, and they were not responding to the commands the same way, and I was just getting like nonsense behavior out of one of the O drives, and it took me quite a while to realize that it was because the firmware was mismatched. So now that's in there, so every time the system boots up, just once, quickly, we just check, yep, all the O drives are on the same firmware, we're all good, let's move on. And if they're not, then it will like flag and a warning and do all these things. Another big quality of life improvement for me is interacting with Jugglebot over USB. And this is useful because there is a pretty good O drive GUI. I've started using my Jugglebot GUI a lot more because I can just pan through this data so easily. And I've got to show this just one more time, just how good this is. Like I can like zoom into this data, I can plant markers and see the changes between them. We can change the data that we're showing after it has been recorded. So if I'm like, oh, actually in that recording, how was the current? And actually, in fact, we actually didn't run Jugglebot, so we can just turn off all of those legs and only have the ball butler pitch and the hand. We don't have any plots for the ball butler yaw. I didn't really feel like that was too important. That's the only axis that's not driven by a brushless motor, so we don't have as much data about it. So yeah, I've kind of left it out of the plots. But we can like, okay, if I want to see what the current was, if I want to see what the voltage was, I can just flick these on and off, and oh, it's so good. It's beautiful. It's amazing. So I've kind of been using this GUI a lot more than the O drive one, just because it's a bit more like customized to what I'm actually doing. But the O drive one is still good, and it's still useful to do certain things. But one thing that really irked me previously is that I had each O drive on Jugglebot's base had its own USB cable going to it, and that was then going out, and so I had 6, 7, actually including the hand, USB cables just kind of like around on the floor, taking up space. I would have to always remember to use the USB isolator every single time I was connecting to one of them, and so doing things like changing a parameter in the firmware, I would go down, plug in one of them, stand back up, go to the computer, change it, kneel back down, move the USB over to a different one, stand back up, change it. It's driving me mad. So I've made I don't really know what the best way to show this is, but a thing, oops, that was the wrong button. I've made a way to plug in all of them at once, which looks like this. So as always, this CAD is in the description as well. It should be. It will be at the end of the stream if it's not already. So basically the problem here is that if you straight up plug a USB, maybe I should, yes, step back a sec. One thing that is difficult with systems like this is that if you have power connected to the O drive that's running the motor, and then you also have your USB cable connected to that, if you don't use a USB isolator, then you can, in principle, have what's called a ground loop happen between your power supply and your computer. And this can destroy your computer. The power can go through your power supply, through the O drive, and into your computer's USB port. And your computer's usually not very happy about having like, I don't know, tens of volts put through its USB port, so it tends to not love that too much. So you need a USB isolator. And so what I've done is I've made this little cage here that holds a USB hub with 7 USB isolators, and these each individually go to each motor, to each O drive, including the hand. So what this actually looks like in practice is, I can show you here. The base is basically significantly, maybe this guy. The base is significantly cleaner than it used to be, where now we just have a single USB cable coming out of it, and then in here we have all 7 USB cables going out to each O drive. So I just need to plug into this one cable, and now I connect, and it's magneted on there, so it protects them all from like a ball landing on them or anything like that. super solid. Yeah, so now if I plug into this one cable, I can connect to all 7 O drives at once, and they will all appear in the GUI. Well, they should. Of course, when I do this live, it doesn't work. All right, well, I don't know why that's not working right now, but you get the idea. They all connect at once, and then I can I can just change through them in the GUI. So I can just say, okay, like, if I want to operate on leg 1, I can do leg 1, change what I need to change. If I want to go to leg 2, I can go to leg 2, change what I need to change, and so on. I'm kind of confused why that's not working now. I did yank this cord before. I might have pulled out that cable on the other side. I need to check that. But it should show them all up in one go, which is so nice. So nice. Very good quality of life. And the base is cleaner, so it's a lot more tidy. Shrimp Pixel says, I learned about USB isolators when I tried plugging in a shitty Ender 3 clone into my PC while it was mid-print. Yes. Thankfully for me, I've actually never had a problem with this, which makes me like, as far as my experience goes, this isn't a real problem because I've never had it be a problem. But I'm still like a little bit like unsure of exactly when I need isolators and when I don't, because I've been very just using, if I ever have a shadow of a doubt, I just use it. Yeah, it's, yeah. I think it's a good problem to not have. Yeah, definitely. And the last little thing is a new GUI, which I've already shown you, so we don't need to spend more time on that. Okay. So now we get into the big stuff. So I went through a bit of a process with deciding what possible control modes, or like, I don't know, yeah, control, yeah. What kinds of processes we might want to use to control Jugglebot's platform specifically. The hand control is very good, that's super solid, but the platform needs better, we need to have a more holistic view of how to move it around, as I've described before. And to my knowledge, I'm just putting this out there in case it's not abundantly clear already, I am not a controls engineer. My controls course in university was easily the worst grade I got in any course, which is, I don't know, kind of funny given where I am right now. But yeah, so keep that in mind. But yeah, so I went through a bit of a process with figuring out what we might want to use. And after a bit of research, this model predictive control, or MPC, kept coming up as a good option for Jugglebot. And the more I looked into this, the more I thought, actually, yeah, this does kind of do exactly what Jugglebot should be doing. And I'm going to try to explain it now. So, as always, if you see anything here that you know is not correct, please let me know. Or if you think it's not correct, please let me know. I am endeavoring to increase my understanding of this all the time. So this is what I've got. So what is MPC? The way that I have implemented this for Jugglebot looks like this. Now, prior to the MPC itself kicking in, we have a look at, we basically take our commanded pose. So we say, okay, we are here and we want to go to over here. We take this commanded pose in pose space, so like X, Y, Z, and then the rotation. So this is not looking at any of the legs. We take that pose as I could command it to Jugglebot, to like move here so that the ball is in the right spot. Like that's easy to compute. We take that target pose and we fit a quintic polynomial for each degree of freedom. So like X, Y, Z, roll, pitch, yaw. We fit a quintic polynomial to get us from where we are right now to where we want to be. And that is that's our target path for what we want to be following. And then the MPC itself, at a given time, it can look ahead up to 1.375 seconds into the future to see what all of our upcoming targets might be. So we say, like, if nothing is happening for the next 2 seconds, we're just sitting here waiting, doing nothing, if something happens in 1.5 seconds, we're just sitting here waiting, doing nothing. As soon as something comes into this window of 1.375 seconds, then we kick into action and we say, oh, we've got a target on the horizon. We need to get to that target by that time. This time horizon, if you're curious, is broken up this way. I'm not going to go into too much detail there. And then we're still at this time instance. So let's say we've got a target that is exactly 1.375 seconds in the future. We solve the full 6-degree freedom pose and the leg trajectories simultaneously to get us from where we want to be to that target in 1.4 seconds to best meet all of our kind of like target constraints. And some of the things that we weigh against are the tracking error. So we want to make sure that we adhere as close as possible to this, to the quintics that we, to these guys. We want to adhere as close as we can to those. But we also want to make sure that our velocity and our acceleration is what we expect it to be. And importantly, we want the control effort to be quite low as well. And things that make the control effort higher are if we're putting the platform into positions where it's kind of unstable. That requires more computation to figure out, is that stable or is that not stable? Whereas if it's like, if it's sitting where it is right now, it's like, okay, that's stable, easy, we can work with that kind of easily. We also include the actuator lag because there is a very slight lag between when we send a command and when the actuator actually starts moving. I believe that's around 40 milliseconds, but you'll see, yeah, more tuning is required. But then also we do want to make sure that we are including things like the mass and the inertia to make sure that we are obeying, so to make sure that we're moving in a way that kind of takes those into consideration. But those are actually handled downstream by a system that computes feed-forward terms that then go out to the individual O drives. Now, there are limits. So this stuff is kind of taken into consideration by the MPC directly in the velocity and acceleration tracking. There are rate limits on how quickly the velocity can change and how quickly the acceleration can change. And those are just like set limits. Like velocity can't change by more than X amount in a given time. So that kind of handles some of the kinetics, but the majority of it is downstream when we're calculating all the feed-forward terms. Now, what happens next is, when I first learned about this kind of blew my mind a little bit. So we have, to kind of recount where we're up to right now, we're at this time step, and we know that in 1.375 seconds, we need to be at this given target. We have planned the full trajectory from where we are right now to where we want to be at, in my case, it's 40 hertz, and that 40 hertz is dictated by this fine step. So we can fit 40 fine steps in 1 second. So that's our kind of like refresh rate. So we've sampled at least 10 times. We've got, for each of these steps, we've got 5 fine steps and 5 coarse steps. For each of those steps, we have the solution for where we want the leg actuators and the platform pose to be at that specific step the whole way along to 1.375 seconds. But then we just chuck it all away. It's amazing. What the heck? So we take the very next step. We don't throw it all away. That was a bit hyperbolic. But we take the very next step that we're going to. We send that out to the motors to say, all right, you do this right now, because that's the next thing you need to do. We keep the one after that for reference a little bit later, which I'll get to in a sec. And then all of the other ones, all the other 8 steps that we've got, that we've just worked, 80% of the work that we've just done to compute them, we just get rid of it, gone, don't want that anymore, in the bin. And every 40 hertz, we do this again and again and again and again. It's amazing. The reason why we keep the next step is because we use that to inform all future, well, like at least the next cycle of this. So when we are like, it's not at that stage. My understanding again is kind of a little bit hazy here, but when we are going through this step of solving from like where we are now to where we want to be, we take the solution from the last time that we solved this, and that can kind of like, it gives us, it's referred to as a warm start. So it kind of gives us like a bit of a head start into this solution. So we say, okay, we are here. Last time, like what, 25 milliseconds ago, we computed that our next step should be this. Let's assume that that's probably going to be the case, and let's start like working off of there, and that can kind of save us some computation time because we know roughly what we're going to want to do. Now that might change if a new target has appeared within this time horizon window. If some new target has appeared, then we can say, okay, this new target is here now, so now we actually need to differ from what our last plan was. We need to update our plan and go somewhere else. But if nothing has changed, then we can probably just take what the last solution was and build off of that. So this warm start allows us to kind of save time once the system gets moving. But then, of course, this is only operating at 40 Hertz. And maybe that's fast enough for the motors if we send this command out to the motors. But to be honest, I should probably have tried that, but I actually didn't, because every time that I've been using direct control of the motors, by which specifically I mean pass-through control, so I'm telling the O drives, I want the motor to be right here, right now, just get there. And they just do as much as they can to like track the commands that I'm sending to them. This gives my code the most control authority over the robot, but it means that I need to be really kind of careful with what commands I'm sending out to it. And if I was only sending 40 Hertz commands in this way, the O drive runs at 8 kilohertz. So it's sitting there for a long time in its own time reference, just sitting there waiting. We go, oh, there's another command in. I action this command. I shoot my motor to where it needs to be as quickly as I can. And then 25 milliseconds later, I get another command. And again, I should have actually tried this, but my very strong suspicion is that this is going to lead to very jerky motion. It'll be too stepped. We kind of want this to be, I would guess, at least around 100 Hertz, ideally more. But the reason why I haven't increased that rate, let me get rid of me so you can read the whole thing. The reason why I haven't increased this to 100 Hertz is because this is a lot of computation. There's a lot going on in here, and it's just too much for my computer to handle, which, keep that in mind, we will return to that soon. So I actually started at like, I think 60 Hertz and then have been progressively dialing it back to now we're at 40 Hertz. But we want faster commands to be able to send out to the motors. So what we've got is another layer of interpolation where we're taking each subsequent MPC command and interpolating that into 500 samples, or at 500 Hertz, to then send those commands out to the motors. And yes, the end result is that we have 500 Hertz commands per leg for the position and the velocity feed forward and the torque feed forward. And in principle, this should result in very smooth, very holistic motion where the platform actually does what you would expect it to do. And I've witnessed this once. I actually haven't been able to find, I haven't spent enough time trying to find my recording of this, so I can't show you this right now, but I can describe it, where as soon as this happened, I realized the problem that I was having with my old control mode. And I kind of described this before already in the stream. So what I was doing before was just having the platform go like straight to its target. And it was like if it was going Z, like along the X direction, it would just be doing like this kind of thing. And it was very, like every time it would arrive, it would kind of shake around for a little bit. And it was obviously not a good way to go. But without me trying to have this happen, just because of the way that this control system, like the MPC works, when it was being commanded to move side to side, it would actually lean, move, and then lean to like absorb the motion. And each leg individually was working a lot less. Like it was a lot smoother control, it was a lot smoother motion per leg, as well as the platform not actually jittering around. And it was so, I was like, oh, this is beautiful. This is amazing. Yep, if only it worked so well all the time. So unfortunately, this is not as easy as I had hoped. And I wasn't expecting this to be like easy. I knew this was going to be difficult, but man, there are a lot of knobs that can be tuned in this system. We can change the time horizon, which sets the cycle rate, as I described before. We can change the model that we have of the actuator. How much lag time is there between when we send the command and when the actuator actually starts? How do we weight the different costs that we have? We want to track the command, but we also want like global and local smoothing. It's like smooth control, smooth movement. We also want to make sure that we're within all of our constraints. So we cannot, at any point, we cannot exceed the stroke limits of the actuators because that will break them. We shouldn't exceed the velocity limits because, I don't know, you need to be able to slow down at the ends to not smack into the ends. And we have acceleration limits because if we try to accelerate too quickly, then we're going to put undue force on the motors and the string's going to slip. And those are problems that I haven't actually encountered, but they might happen if we do this too much. But then we also have the solver budget. We also have friction. And now this was actually a very interesting thing. So one arc that I went through in this process, there were many arcs. Claude actually picked out 8, but I'm not going to go into all of them. One of these arcs was on friction and this idea of the lag of the actuator. And where this was coming up is that I would tell the robot to move, or tell the platform to move, and it would stay stationary for, I think it was like 200 or 300 milliseconds, and then it would start moving consistently. And my thinking was it's probably related to cogging torque, because having felt these motors for a bit, like I've got a test leg here, having felt these motors that I'm using in the legs, there is quite a bit of cogging torque. So you can kind of see like where my finger, like I'm like holding the motor so that I'm not slipping against it. And you can see like it wants to like sit in these like detents almost. And that's to do with the way that the motor is created. And I was thinking that because that motor torque is so high, maybe we need to kind of overcome that with like a bit of a kick to get moving. And then once we're moving, it's fine because it all averages out. Claude didn't think that was the case. Claude thought, no, it's probably not cogging torque, it's probably friction, which in hindsight does make sense because we have 3 pulleys in each direction. So a total of 6 pulleys in here to convert from motor spins to carbon fiber rod goes in and out. So 6 pulleys, that's a lot of opportunity for friction. And long story short, we went through a whole bunch of tests where I had this test leg on basically like on here. Thanks to the beauty of Arca Swiss plates, I can mount whatever I want on here. Wow, beautiful. But I had that leg on there and we ran a whole bunch of tests to see what might have been causing this problem. And long story short, it was absolutely Coulomb friction with an R squared of like 0.95 or something ridiculous like that. It was like, without a doubt, friction was the cause of this problem. And Claude was able to fit a friction model to this with, I'm blanking on the name of it right now, what the friction model is, something Strybeck, I think it was a Strybeck model, to try to model what this friction is so that we can kind of compensate for it. And that kind of seemed to work, but I could never really get it to work really nicely. And actually, I want to show a demo here because I want to show you what I have been witnessing. So let me fix up my cameras for a sec. That was not the right one. There we go, that's better. I really, really cannot wait for AI to be able to do this kind of camera control for me. This would be amazing. Nope. Come on, looks like I might need to clean that lens. All right, there you go, so now you can see Jugglebot. So let me move this because we don't need that anymore. Let me plug in Jugglebot. And yeah, I'll turn off Butler because we don't need that anymore and turn on Jugglebot. All right, so Let's go to VNC. We tidy this up a bit. We want Jugglebot launch, so let's launch that. And then we want to be sending MPC commands. Okay, so, all right, Jugglebot is going through its homing sequence now, so you can, there you go, you just saw the end of it. All right, so the way that I've set this up right now, the way that this would work in actual operation is that when the launch file is run, then it would start up the MPC commander, and that would just be sitting there waiting for poses to come in. And then as each commanded pose comes in with a timestamp of like when we need to be there, then that MPC that's constantly running all the time will take that in, add it to our time horizon, and then when it becomes relevant, like if we send a thing that we need to be somewhere in like 15 seconds, we can kind of chill out for a bit. It doesn't take that long to get anywhere with the Jugglebot the way it is right now. So we can kind of hang out, and then once we're in that 1.375 second window, then we kick into action and actually move. But while I am still doing testing, I have the MPC being commanded separately. It's like a standalone thing. So I can run multiple sessions and I can change things between each session while leaving roles open and that kind of thing. So it's a little bit convenient that way. So I'm going to start off, I always like to start off just by sending a simple, like stay where you are. But of course, where it is right now is not at Z is equal to 170. So we need to get it there first. So let's go to, let me show you in the GUI. So in the GUI, I can activate, and that raises the platform up. And actually now we don't need the ball Butler stuff, so we want to show all the legs again. So let me turn all the legs back on. There we go. Not that we really need that too much. We can also see the mocap markers in here. It's amazing. It's so good. There's ball Butler. Ball Butler's been positioned where it's supposed to be, up on the shelf. Oh, I love this GUI so much. Anyway, so my first command that I'll send on the MPC is just nothing. Just stay where you are. So as we expect, nothing happens. And that will last 5 seconds. So it'll sit there 5 seconds. Cool. We know that nothing is egregiously broken, at least. So now I'm going to send, and you can actually see in here, I'm going to show you all the dirty little details. We're getting a lot of OH spikes. Something has changed recently. I'm not too worried about it for reasons I'll get into a bit later. So I'm going to send go to 30. And keep in mind, this should be just a move straight down. We're moving down 140 millimeters. Should be really smooth. We've got 5 seconds to get there. Let's go. Yeah, not great. Let me actually put this down so you can see it a bit better. Not great at all. That one didn't actually get the whole way down. So let's try running that command again. So it'll go from where it finished. Yeah, yeah, yeah. Not good. Not happy. And we're getting lots of solve failed errors, and lots of other kinds of errors. So I'm going to call it there actually, and we can deactivate the robot, bringing it down. Now it's all tucked away. So this clearly is not working. But the question is, why? Why? And this is where I've been for the last maybe 3 months. Yes, welcome to my life. There have been some significantly more aggressive movements than that. There was one string that broke, one what I'll call a catastrophic failure, where the system, I don't know, I can't remember exactly how this happened, but it was commanding itself to move down like immediately, like go from 170 millimeters down to 0 right now, and it slammed the whole thing down. I do have a recording of it, so I'll show that in the video, but man, that was not good. I'm so glad that only one string broke and not more, because that was very tedious to fix. So I want to talk about my Claude workflow, but I want to do that later actually. Okay, no. So what I want to show you now is, as you can see, that doesn't work. And as I've mentioned, there are a crazy amount of knobs that I can tune here. And this is what I've been doing for the last like 2 or 3 months. I would run a session, I would see how that went, change a couple of these knobs, run another session, see how that went, change a couple of the knobs, rinse and repeat again and again and again and again. Many, many, many times. I've probably got hundreds of clips of me trying various things. Yeah, lots and lots and lots of attempts. But just recently, I've realized maybe my problem is that I'm compute limited, which might explain some things. And what I mean by compute limited is that, as I said before, this process, all of this is quite compute intensive. And as I mentioned, I started off with a refresh rate of quite a bit higher than 40 Hertz. I think it was like 60 or 70 at the start. It's definitely more than 40. And then I slowly worked that back to now it's 40. And according to Claude, you don't really want to go too much less than 40 because then the planner just doesn't have enough like authority to make changes as it needs to. So 40 seems to be kind of like on the slower end of what is acceptable for model predictive control. But again, I'm not an expert, so I would love alternate thoughts if you have any. Yeah, so I started looking into what is actually going on the Jetson while I'm running this. And keep in mind, this is running on a Jetson Orin Nano dev kit. This is my computer. And we can see some problems here. So this is just a report that Claude made for me earlier today. It's not exactly how I would have formatted things, but it is good enough for the purposes of this stream. And my Bluetooth just disconnected. All right. Good thing this is a touchscreen. Okay, so in this first chart, we can see this orange dotted line, the horizontal dotted line, is the budget that we have for making these solves. And we can see that we have three tests here, S1, S2, and S3. S1 and S3 are identical, except that S3 happened after I rebooted the Jetson. Other than that, it's running the exact same code. But S2 is the same as S1 before the reboot, except that in that one I have turned off the hand timer because I was under the suspicion that in the ROS network, one of the things that Claude picked out as like being a cause for CPU burn is that I've got a heap of timers running in my CAN handler, and one of those timers is for Jugglebot's hand, which I'm not using right now, so I can probably turn that off. And what that does is that runs at 500 Hertz every single time. When it's running, it will receive the feedback from the hand motor and take that feedback, pass it, and then send it off like to the GUI or elsewhere. And that runs 500 times per second. So what I did is I figured, okay, maybe that's creating quite a burden for the system. Maybe I should just try turning that off, given that I'm not using it right now. So that's what the S2 run is. And you can see, I don't know, maybe there's a difference there. I don't think that would be outside of the error bars. Interestingly, the reboot seemed to help, but not by a huge amount. And we can see that we do have a considerable number of solves that are beyond the budget that we have. So we can see we've got the mean is the blue, the P95 is like 5% of the solves are worse than this, and the max. And so we can see we have 95% of the solves are, I don't know, just over budget. Not great. Not great at all. Yeah, we really want to be below budget all the time. And we can see, in the zooming out kind of big picture, we have 600% CPU capacity because we have 6 cores and each core can have 100%, but we're demanding 800% because we've got all this stuff running. CAN node by itself is one entire CPU core running 100% with like the fastest speed that it can possibly run at. Just the CAN node is one entire core of this computer. The model predictive control is 80% when doing simple commands like what I showed before, just moving down, moving up, moving to the side. Very, very, very simple stuff is like 80% of a core. I need to do a little bit more looking into what this VS Code plus extension, like plus other stuff is, because I wouldn't expect VS Code to use that much. I do kind of think that maybe there's a chance at least that this data being shown right now is a little bit contaminated because I typically have multiple Claude sessions running at once, and I have actually had multiple instances where one instance of Claude is running some tests and then another instance of Claude is oh sorry, one instance of Claude is running some tests. Another one is like the one that I'm talking with about the given session. And then I run a hardware session, but the hardware session goes really badly and the solve keeps failing and everything like that because the tests are also running at the same time. So I started getting into a really careful regime of ensuring that if I'm ever running any MPC testing, I need to make sure that all Claude sessions have stopped because there's just too much contention for the computer. And that probably should have been a flag that I was running into CPU problems. And I don't know, zooming down a bit further, we can see CAN node is doing a lot of stuff. It's got 1700 callbacks per second. It just keeps going and going and going. And yeah, so we can see here, this is a good example. With MPC running, so we're sending out all of these commands to the legs as well. If those legs are being commanded, then the expected workload on the CPU is around 1.6 to 2.4 seconds per second. So that cannot work. You can't do 2.4 seconds of stuff in 1 second. There's not enough seconds for that. It doesn't work. Yep. So this is where I'm at right now. Is that actually there's one more thing that I actually want to show that does a very good job of describing this the situation that I've been in. Let me go like this. So this layer down the bottom is where I have spent most of my time in the last like 2 months or so. Is down here, fixing these problems. If like there's a deadlock, when the warm start goes wrong, basically, it would just freeze. It would do very weird things. There's a lot of details in here that I would have a hard time getting into right now, just not in the right mind space. But yeah, I've spent a lot of time going through each of these little problems, saying, okay, here's a little problem, let's fix the problem. Here's a little problem, let's fix this. And they all seemed to work. In isolation, fixing these things did make improvements. Like where the controller is right now is a lot better than it was previously. I mean, the example that I just showed in the stream, this is particularly bad because my ROS system on the Jetson is a bit kind of like in between a couple things right now, so I need to consolidate that before it would actually work properly. But it was improving incrementally, and it looked like it was going well. But the more that I considered that the Jetson is just being overburdened, the more I realized that maybe I'm just barking up the wrong trees here. Maybe I'm spending so much time, and like just seeing it drawn in this graph makes it like Claude is using this information to generate this graph, so it's a bit kind of like circular. But yeah, I should have been focusing my attention on the root cause, which I don't know for a fact, but I'm very strongly leaning towards this being a CPU overburden. There's just too much to do and the computer just can't keep up. When I was instead dealing with all of these little individual problems, which maybe it's possible that if I just had a faster computer instead of the Jetson, maybe these problems would just disappear. And there is one thing that I would be remiss if I didn't flag, is that for one thing in particular, like specifically for the CAN handler having so many timers and so many things to be responsible for, Claude did say that like, yeah, even if you do get a faster computer, that is not going to address the actual core problem here. It might just mask it, because if you get a computer that's fast enough to do what you need it to do, then there won't be any observable problem, but still the CAN handler is probably doing a bit too much. So maybe it's worth kind of figuring out a better way to do that. But still, if the problem's gone, then as far as I'm concerned, the problem's gone, you know? Like, there's no need to fix it if there's no problem anymore. So that's kind of what I'm thinking. Sorry, I just gotta let Cat in. Come on. Here's Albie to say hello. Yes. Yes, yes. Okay, come on. All right, so before making any big commitments to getting a different computer to run on Jugglebot on, I do want to do a bit more testing just to be certain that this is actually the main bottleneck that I'm hitting. But that said, it is pretty fun to look at what possibilities are out there. So I've done a little bit of looking around, and what I've landed on is this guy, Helix 401. Albie, you're too annoying. Sorry. Helix 401. It's amazing. It looks so good. It's like 4 times faster than the Jetson is. You can add CAN to it natively, which will be very nice. I won't have to deal with the weird hackiness that I've done on the Jetson. Yeah. The reason I'm mentioning this now is, I don't know, if anyone has any experience with these like industrial computers or has any suggestions at all, specific, I mean, ideally, if you've had experience with this specific one, I would love to know. But yeah, this is kind of where I'm leaning towards, but it's very expensive. And the model that I put together of like what I would actually want was like $3,000 US, which is something like $5,000 Australian. So I'm kind of postponing that one for a little bit because that's kind of expensive. But there's so many good like improvement of life things that would come along with this. Like the Jetson is an ARM system, which if you have any experience with that kind of thing, you would know how much of a pain in the ass that is. Like I can't update VS Code easily. I always forget how to do it, and I have to ask Claude every single time, how do I update VS Code? Because there's some like weird fucking like incantation that I have to recite every single time to actually get it to update properly. I can't just like click the update button. Stuff like that. If I got an x86 computer, would just disappear. Lovely. But I digress. Yes, so where I'm at right now is that the model predictive control stuff, I am quite confident that is the future of Jugglebot. That in principle, if we can get that to work, then I feel very good that that is what Jugglebot needs. We need a way to have like this method of operation of having a time horizon that we're looking into in the future, and anytime something appears in that horizon, we have to take that into consideration and adapt what we're currently doing to meet that change. That is like exactly what you do when you're juggling. If you have a collision in the air and you say, whoop, all of a sudden, I was going to go for this ball, but now I'm going to go for this one first because then I can make that one afterwards. Jugglebot can't hold multiple balls in one hand, but that's a separate thing. But that's exactly what you're doing there. You're saying, oh, my plan was this, now I need to quickly, instantly change my plan and go somewhere else. And model predictive control, as far as I'm aware, seems like an extremely capable way of making these like real-time decisions of what to do when. The problem is that it just needs a lot of compute. And maybe I can optimize my system a bit better, but for the time being, I've decided I've gone too far down that rabbit hole. It doesn't look like there's going to be there's no obvious way out except for paying $5,000 for a new computer. I feel quite confident that that will significantly help and like unblock some things. But that's $5,000 that I don't really want to spend on this right now. So what I'm doing instead is I thought I wrote this down on the slides. Instead what I'm doing, I am trying to focus on my goal for the Ball Butler video, is to make the Ball Butler video. And what my plan is for this, because Ball Butler works. Like once I apply that affine transformation and get the timing to work correctly, which I feel pretty good, is just a matter of tuning some things. Ball Butler, as far as I'm concerned, is done. It can reload, it can throw to where I want it to go. It's great. But I want the video on Ball Butler to be, you know, kind of exciting. I want to show why I wanted to make Ball Butler, not just the fact that it works, but I want to show exactly what the utility of it is. And in my mind, the intersection of not too crazy hard and also clearly showing what Ball Butler can do is 2-ball juggling, because Jugglebot has already done 2-ball juggling. I've shown that off in a video a very long time. I realized it was like 2 years ago now. It's a while ago. But Jugglebot has been able to do 2-ball juggling. But you may remember that was just with me manually feeding the ball in, and it was super sketchy, very dodgy, not great. So what I want to do is, for the Ball Butler video, I want to have even just one shot of Ball Butler throwing the ball down to Jugglebot. While that ball is in the air, Jugglebot throws another ball up, catches the one the Ball Butler just threw, and then goes into 2-ball juggling. And if I have that shot, that's like close frame, video done. Well, development done enough for the video, and then I can go into video editing mode and make that video. So I want to get it to that point. And this whole MPC stuff has just been kind of a digression because that's where I believe that things should be going into. And I was hoping that I could get the MPC working enough to get the two-ball juggling from Butler to work, but it seems like that's not going to happen. So what I've just decided in the last couple of days, this is a big motivation for why I'm having this stream now, is that I'm kind of at a decision point here. I can either continue trying to optimize MPC and probably just smash my head into the wall for another couple months, or spend $5,000, or both. Or I can cut my losses for now, temporarily put a pause on MPC, with a plan to come back to it later, because again, I believe that it's the right way to go. And then spend my time focusing just on open loop control, which is basically what I was doing before, except now we can take what I've learned from MPC with the whole like leaning into the move to kind of make the movement a lot smoother for the legs and the platform. If we can pre-plan everything that needs to happen for this whole sequence, then we should just be able to like hit run and it will just run. And I could remove a ball from the system and I wouldn't know, it would keep going, but it would be fully open loop, but it should work. And as far as the YouTube video is concerned, that's all that matters. So to that end, we've been working on simulation now. So my current position is I'm committing 100% to the open loop control. I've completely put a pin in MPC stuff, and I'm now fully focused on open loop. And one amazing thing that Claude has opened up for me, which I probably could have done myself, but it's just so much easier with Claude, is a simulation. And I want to show you what this looks like. So one thing just before I mention this, Claude was working on this since the stream has started, so I don't know exactly what state this is in, but it should be at least good enough for a demo. All right, where are we? Here, this one. So let me tidy that up. I like to keep my command lines clean. Oh. All my commands have got mixed in. I'm gonna go back through because I can't remember what it is. Here, juggle demo. Let's not do the Apex height for now. Let's see what this does. So now, oh, it's a bit janky. Full screen. So now we've got this MuJoCo demo, which is a physics sim, and it's quite cool. So this is obviously not, as I said, we're still in active development right now, and this is also running at 40% speed, so hence why gravity is a bit weird. And so you can see some weird things are happening here. This is kind of what I'm trying to get it to avoid doing, is like here, obviously the throw will be going off on an angle to the left, but the ball is instead just going to go straight up because, you know, that's how physics works. And the same thing here, the ball just kind of like snaps into the hand, but we're working on it. You know, it's a work in progress. But the idea here is that if we can get this to work in full open loop, then I can take what these commands are from the simulation and just run them on the robot, and we should be good to go. And it should be perfectly like high fidelity, because this does allow you. This doesn't really work while the sim is running, but you can change these positions and like move the robot. I can't do it right now while the juggling sim is going, but as far as I can tell, this is like the fully legit physics sim. Now, where that like fully legit kind of falls apart is that it doesn't handle the contact between the ball and the hand properly. Now, this is why I have waited this long to get into doing simulation work, because I've heard from other people who have done simulations for very similar, like for juggling, that contact is not really possible with today's simulators. Our current, like globally, as far as I'm aware, simulators, like physics robotics simulators, are really good for doing like humanoid robots and like interacting with the ground and like picking up objects. But if you have like this spherical contact between the ball and the hand, and if that's only lasting like a couple hundred milliseconds. And also if it's sensitive enough that the tiniest little difference there will send the ball off in a different direction, it just doesn't work. So what ends up happening here is if you try, in my experience, and I would love for anyone with any physics sim experience to try this themselves. I'll put all right, we've got the link from Claude is now done, and I'll put a link in the description to this stream for some information of how to run this simulator yourself if you want to, and it should run on your system. If it doesn't, check with Claude, and Claude can help you out. But yeah, what we really want to have is, so the physics sim does all of that contact mechanics itself. And it says, okay, if the ball is in the hand and the hand is moving this way, then the ball is going to move out normal to that hand. But in reality, what ends up happening is that because there's that like spherical contact or like line contact between the ball and the hand, in the sim, you can't have that. You can just have point-to-point contact. So that what ends up happening is that the ball jitters around in the hand while it's being held, and then when you go to throw, it goes whoop, and then my last jitter was in this direction, and so now whoosh, the ball is just gone, and it just doesn't work. Now, the problem then becomes, how do you address that? And I've done a little bit of playing around with the sim so far, not the one that I just showed because it's still very janky, but I tried changing this around, so you can change things like the softness of the collision so that the ball doesn't have like energy to make those kinds of bounces, and you can do things like what the simulation was just doing then, where it like snaps into the hand, it's like locked to the hand, and that kind of works, but you know, like it's not representative of like the actual physics. It is, well, it kind of is in some ways, because with this ball with the sand in it and with this hand, it does lock itself in very well, and like once it's settled, it's in. But that's like, if the ball's over here, it's not just going to suddenly snap in real life. And like if it landed here, it will have some time of like centering itself before it lands in, and it would be amazing if the physics sim could handle all of that correctly. But yeah, I haven't been able to get it to work. So my plan right now is to use the physics sim to generate smooth motion back and forth, including the throw in from ball Butler, which I think was kind of skipped over, but it is in the sim. Not with ball Butler's actual position, but that can be changed. Get that sim to work, and then, yeah, run that on the robot and see what happens. And I'm fairly confident that this open loop control should work to be able to get at least kind of as far as it did before. I would like the pattern to be a bit more sexy than the two ball columns that we had in the last video, where it was like the two columns were as close together as they could physically be. That was just so janky. Ideally, I would really want like a circular pattern, like what people normally do when they're juggling two balls in one hand. Or even better yet, I think it would be great if we could do like a kind of crossing thing like this. But this is a kind of a weird pattern. There's a bit of like, I was kind of a bit out of frame there, but hopefully you get the idea. So something like that, or like this, like circles. Something that's not just like columns as close as possible. But we're getting there. Yep. Now, all right, there's one last thing. Actually, looking at questions or responses. Todd Phillips says, if you change the hand from a circle to a triangle, it would then give 3 points of contact rather than a line. And that's true, it would, and maybe it would help. And one thing that I did try something along those lines, not quite that far. I didn't go to a triangle, but I did go to, I think it was an 8. I went to an octagon, where I replaced the CAD, like the URDF file of the hand, or of Jugglebot's hand. I changed it from being a circle to being 8 rectangular prisms, thinking along the same lines as what you've suggested, where I'll have now like 8 point contacts between the sides, but that didn't really help. Maybe going to a triangle, maybe that would be enough, but I suspect that the inherent problem is still going to be there, where it's going to like bounce between those 3 points. It's just going to like do, 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 do. And the thing with juggling is that if you are off, if you're throwing like, if you're just doing little throws, like what I was just doing before when I was juggling, a small amount of error is not that bad, but if you're throwing like 1 meter or 2 meters in the air, if you're off by just the tiniest little bit at the start, then that sends the ball off somewhere else. So if the simulation is off by like 0.5 of a degree, that's too much if you're throwing that high. Like, it's too much in the sense that the system should be able to compensate for that, but it shouldn't need to, because the simulation is no longer truthful. It's no longer doing what the ball would actually do. So then the simulated Jugglebot would have to correct for that. And yeah, I mean, maybe I'm demonstrating my ignorance of like the sim to real pipeline here. There's definitely things in this pipeline that I don't understand, that I would like to understand better, but yeah, it's non-trivial from what I can tell. Yeah. I just want to have a quick little interlude to Albie here. Albie's watching over me, making sure I'm doing a good job. Hello, Albie. Thank you for your hard work. Yep, sitting on my printer like a little rat bag. Anyway, there's one other thing that I wanted to go through here, which is something that I have been refining and using quite a lot, and I would be very interested to see if anyone has any feedback on this or any thoughts on this. And this is my Claude workflow. So there's obviously, yeah, I don't know. There's a lot of hype around Claude and Claude Code and like AI in general, but I want to try to kind of like stay out of that for now. But I do believe, I haven't seen anyone doing a project similar to this with Claude, let alone having the same kind of workflow as what I'm doing here. So I figured it would be worth just kind of sharing this and seeing what people think. So the general idea, the aim is to get Claude as close as possible to the hardware, because this will mean that the iterations will be as fast as possible. And keep in mind, the framing for this as well is when I was doing model predictive control stuff. So to kind of rehash what I said earlier, my general workflow was run a session, which is fully logged, analyze the results of that session, make some changes based on those results and that analysis, and then run another session. And then keep doing that again and again and again and again. And at the very, very start, this was very tedious because I would have Claude on one computer and the Jugglebot was being run on the other computer, and I'd have to like send the data back and forth, and it was very slow to iterate. But now I've got a much, much, much faster workflow. So yeah, we run the hardware session, and then in Claude, I can run /diagnose or /investigate. These are on GitHub as well, so you can check out these Claude commands if you would like to. Claude then analyzes the session using pre-written analysis tools, which are like Python scripts, so there's no option for like hallucination or anything in the analysis stage. It goes through the analysis, figures out what it needs to figure out. If there is data in that session, like if something new happened in a session that hasn't happened before, or if we're testing something different or anything like that, then it will write new analysis scripts to analyze that new data. Claude then writes a report on what happened and presents that report to me, and also suggests what our next steps should be. And this is great. Steps 1 through 4, amazing, that's all good, but there's no kind of like framing for this. It's just a test and it's just results. But what does that mean? And what do we do with that? So all of these tests and all of these sessions are part of a plan. And these plans live in the plan directory. Again, it's on GitHub. I've got a link in the description for like the main repo if you want to check it out. Each of these plans is something that I have figured out before. So like, let's say we might have a plan for fixing the motion onset latency. This was a big one where, as I described, the motors would only move after some amount of time had passed from when the command was sent to them, and we were trying to figure out what was causing that and how do we fix it. And so there was a plan for motion onset latency. And in that plan, there were a whole bunch of different steps and hypotheses and this kind of stuff. And that plan would be constantly referenced by me and Claude as we're going through this. We also have a logbook. These are the plan and logbook. I don't know how to like represent directories instead of the / commands. I'd be open to suggestions there if anyone has them. But any significant finding that we make that is either like the resolution of a plan or just something that's like unrelated to what we were directly doing, but it's just a discovery that we've made, all of that stuff goes into the logbook, which is dated and clearly labeled and clearly described. And that logbook serves a purpose because anytime in the future where we have a specific problem, Claude will then, it's got automatically in its commands, it is required that it will go back through, like if we've encountered a new problem and we say, oh, this thing is happening, why is this happening? Claude will look through all of the old logbooks to find similar instances of this sort of thing happening in the past, and then we can use those logbook entries to figure out what we may need to do this time to address the problem, or maybe it's a problem that was solved but then it reappeared and maybe we just need to reapply the same kind of idea. Whatever it is, we can refer back to that logbook to make sure that we've got a consistent understanding of what's been going on. And using this workflow, it's definitely not as fast as it would be if I just went like write code, go, 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 go. But I don't know how else you could do proper hardware testing without something like this. Doing it this way allows me to run sessions and then have very detailed, very informed analysis of each of those sessions, and then also how it relates to all the other ones. And I've found this to be extremely effective at diagnosing problems and kind of resolving hardware issues, which previously has been very, very difficult to do just with Claude. Yeah, so I'm curious to know if anyone has any thoughts on that workflow. It's an interesting one, and it does run the risk of getting a bit too bloated. I think it might pay off for me to kind of like re-streamline things a bit here, but it works very, very, very well. There's one other command that I should mention, which is I've got a /audit command, which I now have set to run automatically, where it will basically look through everything that it's done and it will audit that code and just make sure that everything's consistent, everything is clean, all the comments are good, all the documentation is updated, that it's all there. And interestingly, pretty much every single time audit runs, it always finds between like 3 and maybe like 15 low to medium scale problems where like comments haven't been updated, or a value was introduced but then later on we decided to get rid of it, but it's still there. Things like that, where it's not really disastrous, but it would be nice to fix. Almost always audit will find something like that. It has found like big issues as well, but thankfully, because the rest of the system is rigorous enough, that generally those big problems don't get through. But if they do, then audit will find them. Yeah, so it's a bit of a process, but I find it works quite well. And I would be very interested to know if anyone else has similar or different workflows for like hardware things, because having workflows for all software stuff is all well and good, but like software's not everything, and integrating it into the hardware is not immediately obvious. Now, one thing I would actually like to mention is what I mean by like getting as close to the hardware as possible. What I would love to have is a system in which Claude can actually directly send ROS commands to the robot. If I could have it so that Claude can interact with ROS and it can run a full session and like send MPC commands and process that feedback and then say, oh, okay, this result happened, like this thing happened, therefore I might want to run this other slightly varied test. It can make those changes and then run it again immediately. And I shouldn't need to like be in the loop directly saying, yes, do this now, no, don't do that now. It should be able to make those decisions itself and run those commands itself. But I haven't figured out a good way to do that so that I can actually see what it's doing. And yeah, I haven't been able to get that to work properly yet. So I'm going through with the workflow that I've just outlined, and that seems to be working fairly well. That said, the MPC still doesn't work. So, I mean, if it's not compute limitations, then there's some serious fundamental problem with the MPC. But yeah. I think your name is Morse code for E, I think, from memory. has said, if you want to edit files on the Jetson, it might make sense to run VS Code on a separate desktop computer and have it edit the files over SSH. Avoids overhead on the Jetson. Yes, you could be onto something there, especially with how the analysis before pointed out that VS Code is using a non-zero amount of CPU power. That could be an option, but that is very similar to what I was actually using at the start, and that's what I moved away from. Actually, maybe I could do it. Maybe I need to just improve my SSH use. Yeah, no, you're right. What I was doing before is I would have VS Code open in both machines, and I would SSH into the other VS Code session on the Jetson from my Windows 10. And in that, I wasn't able to run, like Claude in my Windows 10 VS Code was not able to like access any of the local files on the Jetson. Yeah, okay, I was VS coding. I was SSHing into VS Code, not directly into the computer. That is a very interesting idea. Okay, I will look into that. Yeah, thank you for suggesting that. Also, by the way, there's like quite a lot of lag between me and you guys getting the stream. I don't know, 10 or 15 seconds or something. So apologies for delayed replies. Yeah, so wrapping up, when will the next stream be? I have no clue. I definitely will not be able to return to weekly streams. I think that doesn't make sense for me at the moment. I have too much other stuff going on, like with family stuff and with work, to commit to weekly streams. I don't really know when the next one will be. I'm kind of hoping that the open loop control works without too much hassle, and then I can just get straight into making the video for Butler, which, by the way, I would like to mention my plan here, just to see what people think. So my thinking is to make 2 videos on Butler. The first would be a pure entertainment. I really want to keep it less than 10 minutes, ideally less than like 5, something like what the, definitely not the production quality of HTX Studio, but something along those lines of, I'm pretty sure the channel is HTX Studio, the Chinese makers, they do insane things. Something like that, where it's just like pure entertainment, you don't really get much of an idea of how it actually works, but that's not the point of the video. And then I want to make a second video that goes into all the nitty-gritty details of how Butler works. How each axis is constructed, what the control is, like basically what I would have wanted to have when I was making Butler for everyone. So that way, if you ever want to make anything similar, you can just watch this one video and that will give you a step through of the entire system. How does this whole thing work? Here you go. And yeah, that's obviously, I think both of these videos will take a lot of editing time for very different reasons. But that's my plan, is to have 2 videos kind of focused on different things. Like one's like educational, one's entertainment. And I'm hoping that that should be like a good split. And that way I can kind of focus each one on each rather than trying to make one video that like half does both. So that's my thinking, at least. And I'll be very curious to know what people think. But yeah, so my plan with the streaming is that I don't really have a plan with the streaming, and I will do another one as appropriate. It could be a while, who knows? Yep. I am trying to post semi-regular updates onto Zulip, so if you are interested in like the more data, let's call it like week-to-week goings-ons, then check out Zulip. And if you're curious about what's going on, definitely feel free to nag me and say, hey, what's going on? I do intend on posting there more often, but it always just takes time. And I go, oh, like I want to like do it right. And that includes like adding in plots and adding in links to GitHub stuff and adding in all these other things. And it's like, oh, I don't quite have the plot that I want. I need to generate that plot. And then it just becomes too much. Yeah, it's a whole thing. But yeah, I'll try to post more regularly, but I always say that, so we'll see how we go. But yes, that's about it. Enough rambling. Pretty sure that's everything I wanted to cover. A lot has happened, as I've said. There's definitely stuff that I haven't covered, but will be covered in one of those 2 videos. Yeah, thank you for watching. I hope you found that interesting. I will see you when I see you. And just one more comment from, I think, E. One thing worth looking into if you haven't, it's possible the Jetson might have a high performance mode or micro performance with more cooling. It does have a high performance mode, but I'm already using it. Yeah, it can go up to 15 watts of power, and you can set the clock speed. You can force the CPUs to always use the maximum cycle rate, which I believe I've done. I don't know, the Jetson's so weird. It's like you set a setting, but then sometimes it doesn't update. I don't love the Jetson, to be honest, but it's a lot cheaper than $5 grand. So, you know. Anyway, yep. Yeah, thank you for that suggestion. It's maybe I should double check that that's actually been implemented. Yep. But yes, lots going on and lots to go. We're getting there. But yeah, one thing that maybe importantly, I got a comment on YouTube on one of the videos saying, is this dead? Is this project, is this continuing? And I just want to make clear that no, as long as I'm not dead, the project is not dead. I am 100% committed to doing this, just like Albie's 100% committed to making noise at the wrong moment. Get out of here. Yeah, it's going to happen. It will be a thing. It's just a matter of when. And I just ask that you have patience. I think patience is the virtue that is carrying this project, and yeah, we all need a little bit of patience. You know, we'll get there eventually. All right, with that, I will bid you farewell. Thank you for joining me, and yeah, I'll see you next time. Until then, have a good one.